All right, so next, let us go and define orthogonal groups. ON. Okay. So the orthogonal group ON consists of all n by n real matrices O such that O transpose O is 1. Right? So let's write this in components. In components, this equation is, we take the ijth component of both sides. So on the left-hand side, we have O transpose I, and then another matrix. We are doing matrix multiplication, so there'll be K here and K here and J. And that's equals to delta Ij. So K is a repeated index, and therefore it is summed over by the Einstein summation condition. Are people comfortable with the Einstein summation condition at this point? Okay, so if I write K, what is the range of K?
One, two, three.
Sorry?
1, 2, 3.
1, 2, 3?
1.
Yeah. What is the upper limit? Sorry, I couldn't hear you. Yeah, but we are working with n here. There's not 3 here. These are n by n matrices. So what is the upper limit? Right, so the upper limit is n, right? So the Einstein summation convention basically says that whenever there is an index which is repeated, this summation is implied, right? Okay, so this is an equation. This is a set of conditions on the matrix elements, right? So ON, an element of ON has n squared real entries, right? So from that, we have to subtract the number of conditions that are implicit, that is implicit in this relationship, right? So can someone tell me how many conditions are in this relationship and why? So if I write the so let's write the left-hand side as some matrix M times Ij, and the right-hand side as delta Ij. Now, is this equation symmetric in Ij? Like, if I write it at delta Ji, does this give me delta Ij? Is this the same equation? Do you understand the notion of symmetry, that this is a symmetric tensor? That, do you understand that delta ij is equal to delta ji? Is this something you are familiar with?
Yes.
Okay, so if you are, then can someone tell me if this equation is symmetric or not? If the left-hand side is symmetric in I and j, then the right-hand side is also symmetric, right? So if that is the case, how many equations are here? If I and j go from 1 to n, or small n. Okay. Think about it for a minute.
N square minus n.
N
No.
squared minus n.
Yeah.
Okay, let's look at it this way. So there are two cases when this index is equal to this index. I is equals to I, right? When this equation is, there are two instances of this equation. One is when this becomes the two indices of the same, right? And there is no sum. No sum over I. Okay, so how many equations are there of this form? How many values does I take?
N.
Is it n?
Right, so there are n equations of this form, right? And the original form has n squared equation, right? You know, not counting for independent, just in general, it is n squared equations. So these are the diagonal equations here when I equals to j. Now, when I is not equals to j, when this is true, say I is greater than j, how many equations are there? You can visualize this as a matrix of equations, right? So you had in total n squared elements, n squared equations, but of those n squared, n are taken up when the two indices are the same. So you subtract them because they are not part of this I greater than j. But since this is a symmetric equation, I greater than j and j greater than I is the same. But if you look at just I greater than j, then it would be half of this, right? Because if I look at these equations, you know, these diagonals are these equations, and I greater than j are just these equations. But in total, there are n squared equations, but along the diagonal, there are n equations. So over here, there must be n squared minus n by 2. And over here, there will be n squared minus n over 2. So that when you add everything up, you're going to have n squared. But because of the symmetry, you know, these equations over here are exactly the same equations as this. So we only have to count these. We don't have to count both. Therefore, the total number of equations which are are contained in this set of condition is going to be n plus this thing, n squared minus n by 2. Okay, and if I simplify this, I get 2n plus n squared minus n by 2, or in other words, n squared plus n by 2. Okay, these are the total number of conditions. Okay, total number of conditions. So originally our matrix O of On had n squared real entries, but on those real entries there are this many conditions, so the number of independent parameters is going to be n squared minus n squared plus n by 2. And if I do this, I get 2n squared minus n squared minus n. So I get n squared minus n by 2, and then we have n minus 1 by 2. Right. So the dimension of On is n minus 1 by 2. Is the counting clear?
Yes, sir.
Okay. So let's see that this is actually matches with what we have seen so far. So for example, if I take the dimension of SO2, which is the group of rotation in one dimension, it's going to give me n is 2 divided by 2, 2 minus 1, which is 1, right? In 2 dimensions rotation, you only need one angle to specify rotation. So this works. When we go to 3 dimensions, we saw that there are 3 independent rotations. The rotations in the 3 independent planes, right? Or rotations around the 3 axes. Let's see if that meshes with this, agrees with this formula. So dimension of SO3, the group of rotations in 3, sorry, we don't have to say OS, we can just write O3. Then it's going to be 3 by 2, 3 minus 1. 3 by minus times 2, 3. And what about dimension of O4, which is a close cousin of the Lorentz group? It's as if the Lorentz group if space-time didn't have a time direction, that's what it would be. Here n is 4 minus 1 divided by 2. So we have 2 times 3, 6. Okay, so on and so forth.